Imagine you're on the flight deck of the USS Enterprise in May 1945 in the Pacific. The Air Boss just launched 30 Hellcats and Dauntless dive bombers for a strike on Japanese targets. In 2 hours, these planes will return, low on fuel, some damaged and pilots exhausted. But here's the problem. The flight deck is an 872-foot-long parking lot with exactly one way in and one way out. Every carrier in World War II faced this deadly game of musical chairs. Planes returning from missions had to land one by one on the stern, catch an arresting wire, and taxi forward to park near the bow. It sounds easy, right? But each landing took about 90 seconds, and with 30 planes circling above, their fuel running low, and only 20 minutes left to land, the math doesn't add up. It takes 45 minutes to recover all 30 aircraft, leaving the last planes in the pattern almost out of fuel. And if one pilot misses the wire and crashes, everything halts. The deck crew has to push the wreckage overboard, while the other pilots circle, burning fuel as they watch their gauges drop toward empty. But the real challenge isn't just recovery time, it's what happens next. Once all the planes are back on deck, they sit parked wingtip to wingtip, fully armed and fueled. Want to launch another strike? You can't. Not until deck crews manhandle every single aircraft, moving them around to get ready for the next launch. This process could take an hour or more, making the carrier essentially useless for 60 to 90 minutes after recovering aircraft. Admiral Mark Mitcher, commanding Task Force 58 in 1944, called this the deck cycle problem. His carriers could theoretically handle 100 aircraft, but the straight deck design meant only one major strike per day. The Japanese faced the same problem. At Midway in 1942, Japanese carriers were caught with planes parked everywhere, unable to launch or land when American dive bombers attacked. The Akagi, Kaga, and Soryu were destroyed because their decks were frozen. Trapped in the recovery and rearming cycle, the issue that kept admirals awake at night was this: carriers were meant to replace battleships as the new capital ships, the backbone of naval power. But battleships could fire continuously during combat, while a carrier launching one strike per day was more like an expensive sitting duck. The U.S. Navy projected that, in a theoretical battle with the Soviet Navy in the late 1940s, American carriers would get only one strike before enemy submarines and surface ships closed in. One punch, and then they'd be out of ammo, stuck in a knife fight. The straight deck design wasn't anyone's fault. It's just how navies built carriers from the 1920s onwards. The need for a long, clear runway for launch and recovery went unquestioned until the bodies started stacking up and admirals realized they were losing pilots not to enemy fire, but to fuel starvation while waiting to land. The attack on Pearl Harbor on December 7, 1941, revealed this fatal weakness. Yes, the attack demonstrated how carriers could project devastating power, but it also exposed their crippling flaw. Admiral Nagumo's 6 carriers launched 353 aircraft in 2 waves that morning. By 10 a.m., when the last planes returned, the decks were so clogged that a third strike couldn't be launched. 3 hours were needed to clear the decks, rearm, and prepare for another launch. Nagumo's task force was vulnerable, stuck in the rearming cycle, and he turned for home, leaving his job unfinished. The Americans learned the same lesson the hard way at Midway in 1942. On June 4th, Japanese carriers were caught with their decks full, planes being armed for land strikes, refueling, and recovering. The deck cycle kept them grounded for 47 minutes, which was when Wade McCluskey's dive bombers from Enterprise arrived. In 5 minutes, 3 carriers were destroyed because they physically couldn't get planes off the deck. The straight deck design had turned them into sitting targets. After Midway, both the US and Japan began tracking something called deck cycle efficiency, how long a carrier was idle between strikes. The numbers were grim. USS Yorktown recorded an average of 93 minutes from recovery to launch during the Guadalcanal campaign in 1942. USS Saratoga took 108 minutes at the Battle of Santa Cruz in October. The Japanese were worse. Shikaku took 2 hours and 14 minutes to clear her deck after recovering aircraft during the Eastern Solomons. Every admiral could see the problem. Carriers were spending more time moving planes around than actually fighting. In January 1943, Wade McCluskey, the commander of Enterprise's Air Group, wrote a memo stating that the U.S. was built for one-punch fights, but was in a 15-round battle. In a theoretical naval battle, Commander Walter Boone, a U.S. Navy test pilot, calculated that if Japanese and American carrier groups met in the open ocean, the side that launched first would likely win. The other side would be stuck in recovery operations when the strike arrived, unable to defend itself. Naval warfare had turned into quick-draw duels where the fastest carrier group won. By mid-1943, the U.S. Navy had enough new Essex-class carriers to rotate them, with some launching, some recovering, and others rearming. It worked somewhat, but it meant the Navy needed 3 carriers to do the job that one should have been able to handle. Commander Joseph Clifton, serving on Lexington in 1944, recorded in his log during the Battle of the Philippine Sea that American carriers launched 226 aircraft, but took 97 minutes to recover them all. 5 pilots had to ditch after running out of fuel, waiting for deck space. This system wasn't sustainable. The U.S. Navy was building bigger and faster carriers, capable of holding 80, then 90, and eventually 100 aircraft. But if the deck geometry from 1925 couldn't keep up with these advancements, what was the point of having all that capacity? While the Americans were struggling with this problem in the Pacific, the Royal Navy had quietly found a solution to the deck cycle issue in the Atlantic. British carriers had their own set of challenges: smaller flight decks, cramped hangars, and operations in the harsh weather of the North Atlantic. Captain Matthew Slattery on HMS Illustrious realized that his ship would never match American carrier efficiency using conventional straight-deck operations. So he began experimenting with something seemingly absurd. What if planes could land while others were still parked on the deck? In early 1943, Slattery had his deck crews paint a white line down the port side of the flight deck, essentially creating a narrow landing strip that bypassed the parked aircraft. Pilots would land from the stern, catch the arresting wires, and taxi into the pack of planes. It worked once before a seafire came in too far right and collided with the tail of a parked swordfish. Back to the drawing board. But this experiment proved a key point. You didn't need the entire width of the deck for landings. Planes could land on one section, while other sections handled different tasks. The real breakthrough came from an unexpected source: Dennis Campbell, a civilian physicist working for the Royal Aircraft Establishment. In late 1943, Campbell was studying carrier efficiency and had an epiphany. He realized that the problem wasn't being thought about in the right way. Instead of thinking of the flight deck like a highway with one lane and everyone queuing up in one direction, why not think of it like a railway junction? Just like trains can cross paths at an angle, why couldn't planes? Campbell proposed that the aft section of the flight deck be angled 5 degrees to port. This would allow planes to land on the angled section, while aircraft on the starboard bow could still launch. The Admiralty was skeptical about such a radical change, especially based on a physicist's napkin sketch. However, they approved a trial on HMS Triumph, a light carrier operating in the Indian Ocean where combat intensity was lower. In August 1944, modifications were made to the ship, with only paint and repositioned arresting wires, no structural changes. The first test pilot, Lieutenant Commander Eric Brown, later wrote that landing on the angled deck felt strange, like landing on a carrier that was turning beneath you. But it worked. Brown trapped, taxied left, and was clear of the landing area in 45 seconds. Meanwhile, a Corsair launched from the bow. 2 operations happened at the same time with no interference. The Royal Navy continued testing angled deck operations through late 1944 and into 1945. The results were promising, but still limited. The 5-degree angle helped, but it wasn't enough to completely separate the landing and launch operations. Planes still had to taxi through congested areas. The war ended before the British could fully refine the concept. With Japan defeated, carrier innovation was no longer a priority. The research sat in Admiral D's files, collecting dust as the world demobilized. The solution had been proven in combat, but was forgotten. Fast forward to 1951, when Commander Walter Boone, determined to prove the viability of jet aircraft on carriers, revisited the British reports on HMS Triumph's angled deck experiments. He realized what the Royal Navy had missed. The 5-degree angle was only the beginning. The angled deck wasn't enough by itself. To prevent a bolter, a pilot missing all the arresting wires, from crashing into parked aircraft, the landing strip needed to be angled 8 to 10 degrees. This would allow the plane to throttle up and take off again without hitting anything. The British had been thinking about traffic management, but Boone was focused on physics and failure modes. With the proper angle, a bolter could execute a touch and go, climb out, and come back for another attempt. No crash, no wreckage cleanup, no wasted fuel. In March 1951, Boone pitched this idea to Rear Admiral Apollo Susk at the Naval Air Test Center in Patuxent River, Maryland. Susk's response was simple: prove it. So Boone and his team seized the opportunity to test the idea on the USS Midway while it was in Norfolk for routine maintenance. They painted an angled landing area on the deck with an 8-degree offset to port and repositioned the arresting gear. This geometric change was simple, but the implications were monumental. The angled deck effectively created 2 separate runways on the same ship, one for launches, a straight catapult track from bow to stern, and another for landings. A separate angled landing strip from stern to portside midship. For the first time in naval history, both landing and launching could occur simultaneously. The first test took place in July 1951, with Boone himself flying an F-9F Panther. Approaching at 145 knots, the deck appeared to be turning away from him, but he caught the 3-wire perfectly, taxied to the portside deck park, and cleared the landing area in 45 seconds. While he was still rolling, another Panther launched from the bow catapult. 30 seconds later, a third Panther landed on the angled deck. The flight operations that previously took 90 minutes were now happening in continuous flow. The test crew logged 12 landings and 12 launches in just 18 minutes, what would have taken over an hour on a straight deck. What truly convinced everyone, however, was when Boone deliberately bolted on the 7th approach. Missing all 4 wires, he simply added throttle, lifted off, and climbed away clean. On a straight deck, this would have been a disaster, potentially leading to a crash into parked aircraft. But on the angled deck, there was no risk, and the deck crew didn't even flinch. Boone came around and trapped on the next pass. Watching from the island, the test crew immediately understood what they were seeing. The angled deck didn't just improve efficiency, it eliminated the deadliest failure mode in carrier aviation. The July tests confirmed the geometry worked, and the August tests showed it worked with multiple aircraft types. By September 1951, the Navy's Bureau of Aeronautics was already drawing up plans to retrofit every carrier in the fleet. One test pilot and a can of paint had just doubled American naval striking power. However, retrofitting carriers to make the angled deck permanent was no simple task. It was an engineering nightmare that would take 3 years, cost hundreds of millions of dollars, and force the Navy to rethink every aspect of carrier construction. The challenge wasn't just cutting the deck at an angle, it was that every system on a carrier had been designed around straight deck geometry for 30 years. Changing one thing meant changing everything. The first challenge was the island superstructure. On straight deck carriers, the island sat on the starboard side, about midship, which worked fine when the landing area ran straight down the center line. But with the angled deck, recovering aircraft would be flying directly toward the island before catching the wires. The approach path crossed right where the island stood. Naval architects at the New York Naval Shipyard spent 6 months in late 1951 figuring out if they could move the island, shrink it, or make it transparent to aircraft. The solution they came to was a compromise. shift the island slightly aft, and add a deck extension to the port side to widen the angled landing area. This required cutting into the hull structure and reinforcing frame members. Each carrier retrofit would need 4 months in dry dock just for structural work. Next was the arresting gear. The hydraulic systems used to stop aircraft had been engineered to run perpendicular to the ship's centerline, with wire machinery built into the deck. Angling the deck 8 degrees meant redesigning the entire arresting system, rerouting hydraulic lines, and rebuilding the spaces below deck where the equipment was housed. Grumman engineer Robert Decker calculated that each retrofit would require removing and replacing roughly 40% of the arresting gear infrastructure. USS Antietam's conversion in 1952 alone took 11,000 man-hours just on the arresting system work. Then there was the catapult issue, which turned into an opportunity. The Navy had been testing steam catapults, which were dramatically more powerful than the older hydraulic systems. The angled deck retrofit provided the perfect excuse to install them. Commander C.C. Kirkpatrick, overseeing Antietam's conversion, realized that steam catapults, combined with the angled deck, would allow carriers to launch and recover heavier aircraft simultaneously. But steam catapults required cutting deck plates, running steam lines from the boilers, and building catapult machinery rooms below deck. What started as a simple deck angle project became a complete flight deck reconstruction. Finally there was the mirror landing system, the optical device used to guide pilots to the angled deck. British inventors had developed this system in 1952 using a gyro-stabilized mirror and lights, but implementing it on American carriers brought its own set of challenges. To show pilots their glide slope, the mirror system had to be precisely calibrated to the new 8-degree deck angle, with the mirror positioned where pilots could see it during their offset approach. Lieutenant Commander J.R. Lamb, the test pilot evaluating the system on Antietam, crashed twice in early tests because the mirror placement provided incorrect glide slope information. The mirror had to be moved 3 times before the setup was correct. Between 1952 and 1955, the Navy converted 13 Essex-class carriers to angled decks, each costing between $8 and $12 million, significant when the ships themselves cost $70 million new. USS Bennington entered Norfolk Naval Shipyard in January 1954 and didn't emerge until September. USS Hornet's retrofit took 7 months. These were not minor changes. Workers were cutting away sections of the original deck, welding a new structure, and rerouting every major system. The ships that came out were fundamentally different, even if they looked largely the same from a distance. USS Antietam became the first operational angled deck carrier in December 1952 and immediately headed to Korea to prove if Boone's geometry would work under fire or fail when combat started. The Navy's leadership was divided. Half believed this was the future of naval aviation, while the other half feared it was an expensive modification that would get pilots killed. Antietam had 4 months to settle the argument. The ship arrived off the Korean coast in January 1953 and began flying combat sorties against North Korean and Chinese positions. Commander William Sisko, the air boss, kept meticulous logs, knowing everyone in Washington was watching. The first week established baseline numbers. Antietam launched and recovered 68 sorties in a 12-hour period. This might not sound impressive until compared to USS Kearsarge, operating with a straight deck 50 miles south, which only managed 39 sorties in the same period. Same air group size, same aircraft types, same mission profiles. The angled deck generated 74% more combat power from the same ship. The real difference showed up in what pilots called deck availability, how often the flight deck was ready to receive aircraft. Straight deck carriers in Korea had an average deck availability of 42%. This meant pilots knew they had a 50-50 chance of the deck being ready when they returned. If it wasn't, they'd have to burn fuel circling or divert to an emergency field in South Korea. On Antietam, with the angled deck, availability increased to 79%. Pilots could count on coming home. This wasn't just a statistical difference. When you're in the cockpit watching your fuel gauge, it matters. Lieutenant James Miker, the future author, was flying F-9F Panthers off Antietam in February 1953 when he saw the angled deck save 3 lives in one afternoon. The first incident involved a Sky Raider returning from a close air support mission with battle damage. It came in too hot and bolted through all 4 wires. On a straight deck, it would have crashed into parked aircraft, potentially killing the pilot and destroying several planes. On Antietam's angled deck, the pilot just flew off the port side, dumped fuel to reduce weight, and trapped on the next pass. The second incident involved an F-9F with a hung ordnance, a bomb that wouldn't release and needed to land immediately because the arming wire had pulled. On a straight deck, landing would have been too dangerous with planes parked forward. But on the angled deck, the pilot could land immediately with a clear area. The third incident involved a pilot with spatial disorientation who came in off-center and almost landed on the port deck edge. On a straight deck, he would have crashed into the island. On the angled deck, he was still on glide and trapped normally. By March 1953, Cisco's logs showed Antietam was flying 89 sorties per day, compared to 47 for straight-deck carriers. The Navy sent Captain John Cromlin to observe operations and report back. His cable to the Chief of Naval Operations was blunt. The angled deck increases striking power by a minimum of 85%. Every carrier not modified is fighting at half capacity. Recommend emergency conversion of all fleet carriers immediately. The skeptics in Washington fell silent. What convinced everyone was a new metric. The Navy started tracking in April. Mission effectiveness cycles, which measured how many complete strike recovery, rearm, and relaunch cycles a carrier could complete in 24 hours. Straight-deck carriers averaged 2.3 cycles. Antietam logged 4.1 cycles, effectively operating like 2 carriers. The geometry that Boone had proven with paint in 1951 was now proven in combat by 1953. The combat results from Korea ended the debate. By late 1953, the Navy was committed to more than just retrofitting old carriers. They began designing an entirely new class of carriers, built from the keel up around angled deck operations. The Forrestal-class supercarriers would be the first warships in history where the angled deck wasn't a retrofit, but a foundational design principle. Everything from propulsion to weapons and crew quarters was engineered to maximize the benefits of that 8 degrees angle. USS Forrestal herself launched in December 1954. The difference was immediately apparent when you viewed Forrestal from the pier. The angled landing area was no longer just painted lines on a straight deck. It was integrated into the hull structure, reinforced with deck plating specifically rated for jet aircraft impacts. The island was positioned further aft than any previous carrier, providing pilots with an unobstructed approach to the angled deck. 4 steam catapults, 2 on the bow and 2 on the angled waist deck, allowed Forrestal to launch 4 aircraft every 60 seconds while simultaneously recovering aircraft on the landing area. The theoretical maximum sortie rate was 170 aircraft per day, far exceeding the 90 sorties achieved by any carrier in World War II. Captain Roy Johnson took Forrestal through shakedown operations in 1955, and the ship immediately validated every design decision. During one test evolution off the Virginia Capes in August, the Air Wing launched a 40-plane strike, recovered 32 aircraft from the previous mission, and launched another 20-plane combat air patrol, all within 47 minutes. The deck crew ran 3 separate operations simultaneously: catapult launches from the bow, arrested recoveries on the angled deck, and aircraft towing and fueling in the forward deck park. It was controlled chaos that worked because the geometry kept everything separated. The strategic implications were stark for the Soviet Union. Their naval planners had Assumed American carriers were vulnerable during flight operations. If you could catch them while launching or recovering, you could overwhelm them. Forrestal destroyed that assumption. These carriers were never truly vulnerable because they were never truly stopped. Soviet Admiral Sergei Gorskov wrote in a 1956 assessment that NATO carrier groups built around Forrestal-class ships could maintain continuous strike capability against Soviet positions. His conclusion was bleak. The Soviet surface navy had no effective counter to supercarriers that could launch 100 combat sorties per day indefinitely. By 1959, the Navy had 4 Forrestal-class carriers operational: Forrestal, Saratoga, Ranger, and Independence. Each carried an air wing of 90 aircraft and could generate sustained sortie rates that matched the combined output of 3 World War II carriers. During NATO exercises in 1960, Forrestal's air wing flew 147 sorties in 24 hours, including night operations. The real kicker was aircraft availability on straight-deck carriers. Maintenance crews struggled to work on planes because the deck was constantly cycling between launch and recovery. On Forrestal, the forward deck park became a stable maintenance area where crews could fix aircraft while operations continued around them. The doctrinal shift this enabled was profound. Before angled decks, carrier groups had to stay far from threats because they needed time and space to recover aircraft between strikes. Forrestal and her sisters could operate closer to enemies because they could defend themselves while attacking, launching fighters, while recovering strike aircraft and fueling the next wave. Vice Admiral John McCain Jr. referred to this capability as rolling thunder in a 1961 briefing, meaning the carrier could project continuous, uninterrupted air power like never before. One innovation, one geometry change, had created a weapon system that would dominate naval warfare for the next 50 years. Walk onto any carrier deck today, whether it's Nimitz-class or Ford-class, and you're standing on the same basic geometry that Boone painted on Midway in 1951. The 8-degree angled landing area is still there. The ball catapults are still positioned the same way. The optical landing system still sits portside of the angled deck. 74 years later, no one has found a better solution because the solution was right the first time. That almost never happens in military technology. The USS Gerald R. Ford, commissioned in 2017 as the most advanced carrier ever built, costs $13 billion and includes electromagnetic catapults, advanced arresting gear, and a nuclear reactor that will run for 50 years without refueling. Yet her flight deck with the 8 degrees angled landing area remains the same as Forrestal in 1955. The Ford can launch and recover 33% more sorties than Nimitz-class carriers, but that's not because the deck geometry was reinvented. It's because electromagnetic catapults cycle faster, and the crew needs less time between launches. The fundamental layout that enables simultaneous operations hasn't changed because it doesn't need to. Modern carrier operations now run on a tempo that would have seemed impossible to World War II admirals. During Operation Inherent Resolve against ISIS in 2016, the USS Dwight D. Eisenhower maintained 75 sorties per day for 7 consecutive months. The air wing flew 12,000 combat missions without a single operational loss due to deck cycles or recovery problems. Pilots launched knowing the deck would be ready when they returned. Just as Antietam's pilots had confidence in 953, the angled deck eliminated an entire category of fear from carrier, aviation. But what really demonstrates the innovation's staying power is that every other navy copied it. China's Liaoning and Shandong carriers, India's INS Vikramaditya, and even smaller amphibious assault ships like the America and Queen Elizabeth classes, which use vertical landing jets that don't technically need angled decks, still include the geometry because it improves deck flow and aircraft handling. The design principle has transcended the specific problem it was meant to solve and has become the universal standard for any ship. operating fixed-wing aircraft. The innovation has outlasted the technology it was designed for. Boone was thinking about jet aircraft in 1951, but the angled deck works just as well for the F-35C fifth-generation stealth fighters operating today, and whatever unmanned combat aircraft the Navy will field in 2040. The geometry isn't tied to a specific aircraft type. It's tied to the fundamental physics of landing something with forward momentum on a moving platform. As long as carriers exist and aircraft need runways, the angled deck will be essential. There's something elegant about how a simple geometric change, just 80 of angle, solved a problem that admirals thought would require entirely new ships or revolutionary technology. No exotic materials, no computers, no advanced engineering that only a few countries could manufacture. Just rotate the landing area and suddenly everything works. Commander Boone likely didn't realize he was designing the standard layout for the next century of naval aviation. He was just trying to keep pilots alive and make carriers more useful. That's often how the best innovations work. Solve the immediate problem effectively, and you may accidentally create something that lasts forever. Stand on a carrier deck in 2025, and you're standing on the same piece of 1951, thinking because it still works. The angled deck doubled carrier striking power, eliminated the deadliest failure mode in naval aviation, and created the platform for 70 years of American naval dominance. Not bad for some paint and geometry.